To determine the direction of the force, we employ right hand rule number 1. Point finger number 1 of your right hand in the direction of the force. Finger number 2 to the direction of the velocity of the moving charged particle. And finger number 3 to the direction of the magnetic field.
Let us consider the case of a positively charged particle moving in a uniform electric field so that the direction of the particle's velocity is perpendicular to the field, as in the figure here. The label B and the crosses tell us that B is directed into the page. Let us apply the right hand rule to the particle at the bottom of the circle. The direction of the velocity is to the right. By applying right hand rule number 1, we can determine the direction of the magnetic force, which is upward. The force causes the particle to change its direction and to follow a curved path. If you apply the right hand rule to the particle at other points on the circle, you can see that the magnetic force is always directed towards the center of the circular path. So, the magnetic force causes a centripetal acceleration, which changes only the direction of V and not its magnitude. Let us recall the equation of magnetic force and the equation of centripetal force. Therefore, we can equate this Fm equals to Fc. We can use the Newton's second law to write the equation. This equation says that the radius of the path is proportional to the momentum of the particle and inversely proportional to the charge and the magnetic field. If the initial direction of the velocity of the charged particle is not perpendicular to the magnetic field, the path followed by the particle is a spiral, or we can call it a helix, along the magnetic field lines, as shown in the figure. Let's talk about the notation used by the book. If B is directed into the page, as in the figure on the left, we use a series of green crosses representing the tails of arrows. If B is directed out of the page, as in the figure on the right, we use a series of green dots representing the tips of arrows. If B lies in the plane of the page, we use series of green field lines with arrowheads. If magnetic field exerts a force on a single charged particle when it moves through a magnetic field, you might expect that magnetic forces are exerted on a current carrying wire, which is indeed the case. If magnetic field exerts a force on a single charged particle when it moves through a magnetic field, you might expect that magnetic forces are exerted on the current carrying wire, like in the photo. Because the current is a collection of many charged particles in motion, the resultant force on the wire is due to the sum of the individual forces on the charged particles. The force on the particles is transmitted to the bulk of the wire through collisions with the atoms making up the wire. We can demonstrate the force on a current carrying conductor by hanging a wire between the poles of a magnet, as shown in the figure. In this figure, the magnetic field is directed into the page and covers the region within the shaded area. The wire deflects to the right or to the left when it carries a current. Let us quantify our discussion. Consider the figure, which shows a straight segment of wire of length L and cross-sectional A carrying a current I in a uniform external electric field of B. Let us assume that the magnetic field is perpendicular to the wire and is directed into the screen. A force F equals to QVB is exerted on each charge carrier in the wire, where Vd is the drift velocity of the charge. To find total force on the wire, we multiply the force on one charge carrier by the number of carriers in the segment. That means the magnitude of the total magnetic force on the wire of length L is the force on each charge carriers times the total number of carriers. Recall that the current in the wire is given by the expression shown here. That means we can write the maximum force as shown. Please note that this equation can be used only when the current and the magnetic field are at right angle to each other. If the wire is not perpendicular to the field but is at some arbitrary angle, as in the figure, the magnitude of the magnetic force on the wire is given here, F equivalent to BIL sin theta, where the theta is the angle between B and the direction of current I. The direction of this force can be obtained by the use of right hand rule number 1. In this case, you must place finger number 2 in the direction of the positive current I rather than in the direction of V. The thumb, which is finger number 1, pointing to the direction of force. The current is made up of charges moving at some velocity, so this really is not separate rule. In this figure, the direction of the magnetic force on the wire is out of the page. If the current is either in the direction of the field or opposite the direction of the field, the magnetic force on the wire is 0.